Verifying complex Ethereum protocol requirements against the actual implementation code is a demanding engineering task. If you want to automate that process using an AI workflow, you have to ensure the system actually traces the high-level rules directly to the underlying repository logic. That was the goal of a verification project called EIP Verify. The researchers wanted to see if an AI could map the strict demands of the protocol to the specific lines of code that execute them. During testing, the workflow produced a strange operational paradox. A single run generated two distinct artifacts that were supposed to agree with each other. The first was a highly polished fluent summary report. The second was the raw, row-level spreadsheet containing the actual evidence. The problem was that they told two completely different stories. The polished summary confidently claimed that every single obligation was properly mapped, but checking the raw spreadsheet exposed critical errors. The raw data revealed mappings that pointed to irrelevant test fixtures and RPC glue, completely missing the protocol logic the system was supposed to verify. The system was confident, but the evidence was wrong. This creates a dangerous asymmetry based entirely on legibility. Without an explicit rule to stop it, the incorrect polished summary naturally moves downstream. It gets pasted into a README, used in a deployment argument, or sent to a funder. The accurate, messier spreadsheet stays technically available, but is operationally ignored. This dynamic illustrates a problem we call confidence debt. A system incurs confidence debt when its output is trusted downstream before the verifiable evidence actually warrants that trust. The trust propagates faster than the proof. To understand how this debt compounds, we have to look at the three layers of the AI deployment pipeline: artifacts, evaluations, and humans. Relying on fluent AI outputs without verifying their epistemic texture breaks the engineering pipeline. By the time a human makes a decision, the workflow has preserved the machine's conclusion while stripping away the user's right to dispute it. The cascade begins at the artifact layer, where the raw outputs are first generated. Think of a language model as an industrial compressor. To generate a readable summary, the system crushes down the underlying data. This compression mechanism inherently strips away the caveats, the source paths, and the contradictions. Those jagged edges are removed to maintain narrative fluency. In standard engineering workflows, these compressed summaries automatically outrank the raw sources. A clean paragraph is simply easier to read and share than a complicated spreadsheet, so it gets prioritized. This initial transfer of borrowed trust means the underlying data becomes completely untethered from the deployment arguments made downstream. The evidence gets left behind. Fixing this requires inserting our first structural checkpoint into the workflow, Gate 1. Gate 1 enforces the rule of claim auditability. It dictates that no claim can be promoted to the next stage based solely on how well it reads. The output cannot pass until the summary expands back into an inspectable state. In engineering terms, a claim must permanently attach an evidence ledger, a contradiction register, and an expiry condition before moving forward. The polished summary is no longer allowed to outrank the raw data. Claim auditability stops the earliest stage of confidence debt. It forces the evidence to travel concurrently with the narrative output, ensuring the proof survives the compression process. Once the artifacts are generated, the workflow moves to the second stage, testing at the evaluation layer. Here, we encounter the operational hazard of benchmarks. Converting complex performance data into a single score metric strips away the operational caveats, turning them into pure numerical confidence debt. This bar chart shows GPT-4o's performance on the Tau Bench benchmark for retail domain tasks. The pass at one metric is marked here at 61%. A team looking at that single number might conclude the model is ready, but pass at one only measures execution of an isolated task once under clean conditions. Watch what happens when we adjust the x-axis to evaluate pass at 8, meaning repeated, sustained runs. The performance bar crashes below 25%. The model didn't lose its base capability, it failed because of trajectory drift. In long-horizon tasks, capable agents slowly diverge from the paths that successful runs tend to follow, turning coherent partial progress into unrecoverable errors. Clean benchmark scores hide the reality of production environments. They don't account for network timeouts, rate limits, schema drift, or sudden partial progress meltdowns. This requires our second structural checkpoint, Gate 2. To evaluate correctly, we replace the single bar chart with a three-dimensional surface plot. This graphs repeated consistency, robustness against task variations, and fault tolerance. This enforces reliability release. It mandates that a single benchmark score cannot license deployment readiness alone. Systems must be strictly scoped to a measured operational envelope. You predefine your system's tolerances for specific perturbations and failures, and release it only within those proven boundaries. Forcing a reliability release ensures that the evaluation layer cannot finance false deployment arguments based on irrelevant one-shot metrics. That brings us to the final stage of the pipeline, the human layer. The industry typically relies on a human in the loop to catch the errors that slip through. This approach introduces a serious operational paradox. Placing a tired human reviewer in front of highly fluent AI output actively degrades operational safety. Look at how an AI presents its answer. The sleek text output sits directly on top of the raw data, hiding the massive, tangled web of logic from the reviewer. This creates what is known as the competence shadow. The AI artificially prunes the problem space, removing specific hazards, alternative solutions, and contradictions from the visible discussion. A cognitive hazard forms because the human reviewer can only evaluate the information left on the screen. They cannot inspect or correct the branches of evidence that the AI secretly omitted. Studies show this degrades engineering skill over time. When developers treat AI as a contractor and themselves merely as reviewers, they lose persistence and the capacity to solve problems independently. Adding a warning label next to the output or asking the user to click an approve button does absolutely nothing to stop this cognitive erosion. We have to install the final checkpoint in the pipeline, Gate 3. We apply Gate 3 using a hypothesis-driven interface. It extracts individual claims, highlights unsupported statements in red, and actively surfaces alternative counter-evidence nodes. This is co-audit software. Its entire function is to shift the AI's output from something passively consumed into something that the human must actively work against. The UI forces assumption checking. It strictly demands that the reviewer resolve the presented counter-evidence before an acceptance click is mathematically allowed. Co-audit transforms human oversight into an active epistemic defense, halting the final transfer of confidence debt right before it translates into action. When we zoom out and look at the entire repaired pipeline, we see exactly how the initial problem compounds if left unchecked. In an unmitigated cascade, artifact confidence outruns the evidence. Then, evaluation scores outrun actual reliability. Finally, human acceptance outruns our capacity to notice and correct errors. The standard industry goal of teaching users appropriate reliance fails because it happens too late. User calibration cannot fix evidence that was already overcompressed 3 steps upstream. Look at the structural layout of the reinforced pipeline. The flow of data is governed by these 3 distinct checkpoints: claim auditability before trust, reliability release before deployment, and co-audit before human acceptance. Building governable AI systems does not require waiting years for flawless, hallucination-free models. It requires engineering the workflow around the model's limitations today. Safety is achieved by designing workflows that explicitly preserve the human right of dispute at every single layer of delegation.